Okay, folks, for section 8, I want you to organize your notes just like this. You might want to label it section 8, section 3.8. We're going to do a little proof of the derivative of the sine function equaling cosine. Okay, so one notation for that is the derivative with respect to x of the sine function equals cosine. We've been using it, we've been using this rule. We did a little numerical investigation back in section 6 that we think that's the rule, but we've never done a proof of it. And I think it's essential that you kind of see the proof. You don't have to be able to do it all on your own, but you're going to see a place where some of those trig properties that we studied last year come into play. And I told you about that last year. I said, hey, you don't have to memorize all these trig properties. I'm looking it up in one of my favorite pre-calculus books. Right now it's in the back cover. A lot of college textbooks work like that. They put properties and formulas back, in the back for you to refer to. So when we get to that spot, I'm going to put a big red circle around it because it's kind of like a milestone. We talked about this last year. Now we're trying to revisit the idea a little bit that there are trig identities and formulas that help us with higher levels of mathematics. And this is the point where we're going to use it. Okay, so what do I hope to show you? I'm hoping to show you that the definition of the derivative leads us to the derivative for the sine function. So I'm hoping right here in this box to write cosine of x at the very end. So hopefully we can put cosine of x confidently right there. I'm just rewriting it as the derivative of the sine function. So I appreciate you setting up all these notes and watching my videos. I know they're not the most exciting thing. It's probably not your favorite YouTube video to tune into, but I really do appreciate you watching them. So how do we get started on something like this? You can't factor it because we can't stick 0 in for h. So we're looking for a way to algebraically simplify it. And the first thing I do is I look again in the back of my pre-calculus book, and I'm looking for something about the sine of two angles added together. And it is right, let me just see if I can hold it up to the camera for you. It is right there down at the bottom corner of the back cover. And so it tells me that the sine of x plus h, well, first let's just get the limit notation down. The limit as h goes to 0 of the sine of x times the cosine of h plus the sine of h times the cosine of x. So that's what all of this stuff right here equals right down below. Now, I told you I was going to put a little red mark around it. This is the formula in the back of my pre-calculus book that I really like. And I'm just, trying something out here. I'm going to see if that will help me simplify this h that's in the denominator. Now, we can't forget about this other factor of sine x, or the term, I should say. It's not a factor. So I'm going to put down at the end minus the sine of x. All right, well, I realize that you're maybe saying, well, what the heck? Where's this come from? This is that difference quotient that we talked about, like f of x plus h minus f of x all over h. Getting 2 points closer and closer together and finding the instantaneous rate of change. The h stands for some small adjustment in our x value. So my run is h, and my rise for my slope is f of x plus h minus f of x. And to get the actual derivative, the instantaneous rate of change, because this is just an average rate of change, we're going to let h get really, really close to 0, right? Sorry, I didn't put that's the definition of a derivative right there. It's not maybe the one that you're familiar with. Like the one that we've used a fair amount is as x gets close to c, f of x minus f of c all over x minus c. But this is really the same idea. We're just getting 2 points close together. We're trying to find what the slope approach is. So anyways, how does this help me? It doesn't look like it's going to help me. Well, there's some more algebra that we're going to do. We're going to rearrange things. This is called the commutative property. If I move this guy closer to this term over here, they both have a sine x in them. So here's the first term right there, sine x cosine h. I'm going to put this guy next. So it's minus sine x. And then I'm going to divide the h into that part of the numerator. Separately, from this part, because you can break limits apart if it's just addition and subtraction going on. We can just evaluate the sum of the limits, that whole property. So here's what I'm going to do. I'm going to go the sine of h cosine of x divided by h over here. So I'm going to evaluate these two separately. Well, let's just deal with the more simple one right over here first. Okay, so what the heck? How does this help? Well, look, do you see how cosine of x? I'm going to put red around it. The cosine of x does not have an h in it. So when I evaluate the limit as h goes to 0, I don't have to worry about the cosine of x. So what I'm going to do is I'm going to write it out front of my limit. I'm just going to move the cosine of x out front since it doesn't have an h in it. And now I've got the limit as h goes to 0 of the sine of h all over h. Now, this guy right here, it doesn't simplify. Like I can't do any more factoring. So now we're down to a numerical evidence, if you will. What's the numerical evidence that this guy has a value, or does it even have a value, right? I mean, it might be undefined. If it's defined, then we don't have a derivative. We've got an undefined situation. What we've done didn't help. It could be either one of those, right? It could be like what we've done didn't help, or we don't have a derivative. Well, we know we have a derivative, so there's a chance that what we've done was the wrong thing. So let's go investigate on Desmos. And I don't know how to make this super, super clear. We're going to take this. We're going to evaluate the sine of h over h. But you know how Desmos likes the letter x for its dependent variable. I suppose you could get away with an h in there, but I'm going to make it sine x over x. So I've already set that up on my Desmos. Here it is, the sine of x over x. And I'm going to plug in a number for x. And I'm going to see what the function approaches as a approaches 0, okay? Ooh, it goes undefined when we're at 0. Of course it does, because you can't stick 0 into the denominator, right? So all we're trying to do is figure out what does it approach as we get closer and closer to 0. Well, I think we can just see over here on the graph, the function is approaching 1, right? As we get that point closer and closer to 1, well, of course, it's going up here. As we get closer and closer to 0, the y value gets closer and closer to 1, right? Here it is. Okay, let's make that conclusion right stinking now. So I'm going to put a big 1 through all of this stuff. That stuff became 1. All right, well, what else do we need to evaluate here? We need to see what happens in this 1 over here. So what I'm going to do is I'm going to do a little bit more simplification. And then back to this. You might say, wait a minute, well, what's going on, Nelson? Why are you leaving this one alone? I think I've evaluated this one. I evaluated the limit as h went to 0 of the sine of x over x, or sine of h over h, and it went to 1. So 1 times cosine of x is just cosine of x. Now let's simplify this stuff over here and see if we can do any kind of numerical evaluation. Well, look, they both have the sine of x in them. So I'm going to factor that sine of x out. Sine of x times cosine of h minus 1 all over h. And you notice again, this sine of x doesn't have an h in it. So I'm going to move that out front, and I'm going to write the sine of x times the limit as h goes to 0 of the cosine of h minus 1 all over h, okay? Now I've got to evaluate this stuff right here. And dang it, I wish I would have written, I'm going to try to write the sine of x in red like I did with the cosine of x over there. So let's put that. So I'm taking this sine x and I'm moving it out front and I'm writing it right here, the sine of x, okay? So I need to evaluate this limit now. Let's go back over to our Desmos and keep that in mind. It's the cosine of h minus 1 all over h. And I'm going to try, I feel a little bad about changing it to x in here. So I'm going to try to make it h and just see what Desmos does. See, it's thinking it's a slider. You see that? I don't really want it to be a slider. I want it to be a variable or something I can change. Well, let's just try a little bit harder here. Let's see if perfect. So if I define it as f of h, it'll use h no problem as my variable. And you can see now, maybe it's a little bit clear that we're investigating as h gets really close to 0. And I know it says a down here, but we're plugging a in for h, okay? So that one over there, let's just go back over here and see what I've just done. I just reevaluated this guy, but with an h in it, okay? I feel better about that. Having the x in there might mess people up. So let's change this one. What is it that we're trying to evaluate right now? Cosine. Thanks for sticking with me. Keep doing it. Keep sticking with me. Cosine of h minus 1. That's what I want to evaluate right now. So I need cosine of h, and then I need a minus 1 up here. The minus 1 is outside the I think they call it the argument of what we're evaluating. So the cosine of h, and then we subtract 1 from it. Isn't that what we have down here? The cosine of h minus 1. It's not like we're taking the cosine of h minus 1. We're taking the cosine of h, then we're going to subtract 1 from it. Okay, I think I got it all set up. I'm trying to evaluate this guy right here. Now, oh my goodness, look what happens. This guy goes down towards 0. So it goes to 0 from both sides. No matter where I drag this little point here, it goes towards 0. The y value, see that? The y value is 0. So holy smokes, let's put a big 0. Now, let me put parentheses around it like I did on the other one. Let's put a big 0 through this stuff right here. 0. That all became 0. So let's see if we can finish this off. So I've got this one evaluated plus, look, it's this one plus this one over here. Now, if this goes to 0, this first term, 0 times sine x is 0. And cosine of x times 1 is just plain cosine of x. So all of this stuff becomes cosine of x. Hey, look, we just proved that the derivative of the sine function is the cosine function. Now, listen to me for like another 30 seconds, okay? I like this property when I had the sine of x plus h, I like this property better than the way the book does it. Not better than the way the book does it. The book makes a different choice. They choose a different property for at that step. And I don't think it's as clear as choosing this property that I did. And so if you're interested in seeing a different way of doing the proof, it's on page 109. And they use some kind of half angle formula. I just don't like it as much as this one right here. So to me, this makes more sense that we evaluate those two limits down here. One went to 1, the other one went to 0. The 0 one kind of gets rid of that sine over there, and the 1 keeps the cosine. It's crazy how that works. Now, the cosine proof, the derivative of the cosine, you could try that if you're a super advanced student. So let's say you had like a g of x function, and that g of x function was the cosine of x, and we wanted to get the g prime of x. I want to see if anybody's willing to prove that the cosine of x is equal to the negative sine x. And the function that I think you're going to want for that, again, right down in the bottom corner, but it's a little different than this one that I haven't read. So the cosine of x plus h is going to equal, it's the cosine of x times the cosine of h minus the cosine of h time. Oh, shoot. I'm writing the wrong thing there. Hold on, let me try again. Minus the sine of x times the sine of h. And you notice this little minus sign? I wonder if that minus sign generates that negative right there. Okay, so your proof's almost going to look the same. If you can do that proof of the negative sign, the cosine of x is equal to negative sine x, I'd be so impressed. Why don't you show it to me on Monday if you figure out how that proof works? I'll give you a high five. Maybe I'll buy you a coffee. Hey, thanks for your effort today. There are some difficult problems in the homework. I don't want you to give up. I want you to try your hardest, try and figure them out. Thanks for your effort.